All right, so last time we talked about transformers and we talked about diodes. And so we're going to start today with a brief review of those two things. And we said that we talked about those at the same time because they were both components of power supplies. And today we're actually going to talk about power supplies in lecture. Okay? So this is cool because power supplies are circuits that you guys actually use every day. All right? So far in this class we've been talking a lot about components and parts and theories, but we haven't really touched too much on real circuits that you might find in everyday life. Well, today we're going to do that. Power supplies are something that you probably use almost every day. If you charge a phone, there's a power supply that's doing that. If you run a computer, there's a power supply that's doing that. If you plug in your laptop, that little brick that sits between the wall and your computer, that's a power supply. So power supplies are something that you guys use probably every day, and today we're going to learn how this practical circuit actually works. Okay? So this is pretty cool. I'm excited about that. We're going to talk about three different kinds of power supplies. We're going to talk about a half-wave power supply. We're going to talk about a full wave. And we're going to talk about a full wave bridge. And before we get into the specifics of these power supplies, we're actually going to talk about the goal of power supplies, the overarching idea, the reason that they exist, and then some things that all power supplies have in common. Okay, so we'll start off with the sort of the overall goal and the theory, and then we'll get into these specific kinds. Okay? Bless you. So any questions before we get started? Okay, so then let's do a quick review of diodes and transformers. Okay, so let's start with diodes. What was the main purpose of a diode? What did it do for us?
Like a check valve.
Yeah, a check valve, a one-way valve for electricity. It allowed current to flow through in one direction, but it stopped it from flowing through in the other way, right? So that's what diodes did for us. The diode symbol looked like this. Kind of looks like an arrow pointing in one direction, right? So that could be a reminder that it allows electricity to flow through that way, not the other way. So we said if there's a positive voltage over here and a negative voltage over there, was that forward biased or reverse biased? Forward, exactly. And did that mean that electricity could flow or not?
Yes. It does. Yeah.
It does, yeah. So forward biased and electricity flows. And what do we call it if the voltage is in the opposite direction?
Reverse bias.
Reverse biased, exactly. And then there's no flow. Okay? So if we have the diode forward biased, approximately how much voltage do we get from one side to the other?
0.6.
Yeah. About 0.6 volts, give or take, right?
Depending on the material.
Yeah, exactly, exactly. So if we have a silicon diode, it's about 0.6. If it's a germanium diode, it would be something more like 0.3, 0.4, somewhere in there. Okay? And does that voltage change very much depending on how much current is flowing through? Yeah, just a little bit, but not very much, right? Not nearly as much as it would change if it was going through a resistor, right? So it stays approximately constant, regardless of how much current is flowing. Okay? So that was the main idea about diodes. Any questions about that? Okay. So then, let's talk about transformers. What was the main purpose of a transformer?
Step up, step down.
Yeah, to make AC voltage either step up or step down, to change an AC voltage from one level to another. So the picture for a transformer looks like this. It represents two coils of wire next to each other. And if we put these two little lines in the middle, what do those lines mean?
Iron.
Yeah, iron core, right? So if we have these lines, that means that the coils of wire are wrapped around a form that's made out of iron. And that form channels magnetic fields from one coil into the other. Okay? If there's no lines in the middle, what type of core do we say that is?
Air core.
An air core, yeah, exactly. So that means that the coils are just sort of wrapped around nothing. They're close to each other, but they don't have that iron form to help guide the magnetic field. Okay? So we said that the way that a transformer works is that we apply voltage to one side. And what do we call the side where we're applying the voltage?
Primary.
Primary, perfect. Yep, exactly. You're a step ahead of me. The other side is called the secondary, like you said. So we apply a voltage to the primary coil, and that creates a magnetic field in the primary coil. And then this magnetic field from the primary induces a current in the secondary coil. Okay? So we put AC electricity in, and we get AC electricity out. Okay? Now, we said that the main purpose, or the main use for transformers is to change AC voltage from one level to another. So what is the main thing that determines what, or whether we get more voltage out or less voltage out?
How many coils on each side?
Yeah, right. The number
Ratio.
of coils, the turns ratio. Exactly. So this is the number of coils on one side over the number of coils on the other side. We could call it the number of coils on the secondary over the number of coils on the primary. Okay? So if you have twice as many coils on the secondary, you get twice as much voltage out, right? What about the power? Does the power increase or decrease or stay the same? Yeah, it stays the same. So ideally, power in equals power out. Okay? But now we said that power is current times voltage. So if we get more voltage out and the power stays the same, what happens to the output current?
Down.
It goes down, exactly. So the power and the current, I'm sorry, the voltage and the current sort of go almost like a seesaw. When one goes up, the other one goes down. Yeah?
So how would you, if you needed to boost the current after this, how would you do that?
So you get more voltage out and less current out, but then you wanted to have extra current?
Yeah, so after the fact.
Well, you would have to add more power somehow. So generally, I mean, if you needed more current, you would probably need to put more current into the whole system. Yeah. Yeah. Yeah.
You said ideally power in equals power out. So does that just mean like in a real world scenario there's going to be some loss in there, but it's
Yeah.
relatively small normally? Or?
That's exactly right. I couldn't have said it better myself. In the real world, there are always inefficiencies, so you're going to lose a little bit of power, but typically it's small. So we can use this as a pretty good approximation of what's going on. Yeah.
And in 312, the mass symbol, the ratio was opposite of that NS over NP.
Right.
Why do we do it that way? It's kind of our flip-flop it, and just leave it the way it is, 1 to 2. Or...
So I've seen it both ways. The main equation that's important is that the voltage of the primary over the voltage of the secondary equals the number of turns of the primary over the number of turns of the secondary. So this equation works if it's like that, or if it's Vs over Vp equals Ns over Np. It works both ways. I kind of like it like this because if you have it this way, you can multiply that by the input voltage and you get the output voltage. But either way is okay. Yeah, it's really the ratio that is important. So if we get more voltage out than we have voltage in, is that a step up or a step down transformer? Step up, exactly. And if you get less voltage out, then that's a step down. So this is, in general, what's going on with transformers. Do you guys have questions about that? Okay, cool. All right, so we've done a quick review of diodes and transformers now. And like I said, we talked about those two components at the same time because they're both used in power supplies. And power supplies are what we're going to talk about today. So first, let me talk about the main purpose of a power supply, the reason that they exist. So DC power supplies are the ones that we use most often, especially in electronics, because most of our electronic devices run off of DC power, or DC electricity. So the purpose of a DC power supply is to take a large AC voltage and convert it to a smaller DC voltage. So let's just take a minute to review what we mean when we say large AC voltage. Remember, AC stands for alternating current, and that's because the voltage alternates so that part of the time it's positive and part of the time it's negative, right? So if you were to measure this very, very frequently, at one moment you would see that the voltage was almost zero. A moment later it would be going up, a moment later it would be higher, and then a few moments later after that it would be very high. And then if you keep measuring it, the voltage would start to decrease. Eventually, you would get to zero again, and then if you keep on measuring it after that, the voltage would continue decreasing until it got to a very negative voltage. So, and then it would swing back towards zero again. So, AC voltage changes over time, and it changes in this sinusoidal pattern like this. DC voltage stays the same. So say this is 5 volts. If you measure it at one moment, it's 5 volts. You measure it an instant later, it's still 5 volts. A minute later, it's still 5 volts. A week later, it's still 5 volts, right? It never changes. Okay? So the purpose of a DC power supply is to take a large AC voltage like this and turn it into a smaller DC voltage like this. So the large AC voltage is often the voltage that's coming out of the wall. So it might be something like 120 volts AC. Now, if we measure it on a meter, it would say 120 volts. So when we talk about that, is that a peak voltage, a peak-to-peak voltage, an RMS voltage? What kind of voltage is that? RMS, exactly. So when you hear 120 volts in the wall, you know that's 120 volts RMS. So if you looked at it, 120 volts would be somewhere like this, right? It's less than the peak voltage. It's much less than the peak-to-peak voltage, but that's the RMS. So anyway, that's a quick aside. So we're taking this signal that's coming out of the wall that's 120 volts RMS and converting it down to a smaller level like this. So if you have one of those USB chargers that has the little USB plug in it, the USB plug is creating 5 volts. Okay, so you'd be turning that into a 5-volt signal. If you're charging your laptop, that might be 12 volts or 20 volts. Okay, so depending on the application, your power supply will provide some fixed DC voltage, but it's going to be much less than the 120 volts AC. Okay? So the purpose of the power supply is to take a large AC signal and turn it into a smaller DC signal. Okay? So let's talk about how the power supply actually does this. All power supplies include some common components, and they all take sort of the same approach to going from AC to DC. They basically sneak up on it. They get there by little steps. Okay? So let me show you what I mean. So we're going to talk about the components, the basic building blocks that are in all power supplies. And then we'll talk about a couple of specific power supplies, namely these 3. And we'll talk about the specifics of how the components work for those 3. Okay? So we're starting off with a big AC signal. And we want to convert it down to a smaller DC signal, right? We said that was the purpose of the power supply. So the first thing that most power supplies do is they work on that voltage. They take the voltage from a higher level to a lower level. So what component could we use to take a high voltage AC signal and make it into a lower voltage AC signal? Transformer, exactly. So that's the first part of almost all power supplies, is a transformer. So this takes a big AC signal coming in, and then it turns it into a smaller AC signal. So same frequency, same shape, but smaller voltage. Okay? So that's the first part. Then the next part is that we use something called a rectifier. A rectifier throws away, or basically turns the signal into a signal that is only positive. Okay, so right now we have a signal which has both positive and negative components. The rectifier creates a signal which is only positive. Now, the signal still is really bumpy, right? Remember, our DC signal is nice and flat. So we're not there yet, but we're getting closer, right? So we want to make this signal a little bit flatter so that it looks more like the nice smooth DC that we're going for. So the next component that we usually put in is something called a filter. So what do filters do? If you have like a water filter, what's it supposed to do?
Let some things pass through and keep others out.
Yeah, exactly. It allows some things through and it keeps other things out. So we want to allow the DC part through, but block out as much of the AC part as we can. So that's what the filter does. And it's not perfect, but it allows most of the DC part to go through while blocking out a lot of the AC part. So the signal that comes out of here, out of the filter, looks more like this. Okay, so you're keeping most of this DC part, sort of the average part, but you're blocking out a lot of the AC part, the wiggly part. So it's less wiggly after the filter. Okay, that's the technical term. So then the last stage in a power supply is something called, this is a regulator. So the regulator is a component that does sort of the final polishing off. It takes this wavy signal and gets rid of those little wiggles so that you end up with a nice, perfectly smooth DC signal that you're looking for. So that's how the power supply works. Remember, the purpose was to go from here, the large AC voltage, to a smaller DC voltage. And the way that power supplies do that is they sort of sneak up on it bit by bit. They get closer and closer until they get to the final thing. Okay? So we're going to explore how power supplies work. We've already talked about transformers. Today we're going to focus mostly on rectifiers. So the difference between these three power supplies is mainly in the type of rectifier they use. Okay? So we're going to focus on the rectifiers today. The filter is usually just a capacitor. All right? So the capacitor helps to filter out the AC and allow the DC to go through, and we'll talk about that a little bit. And we're not really going to talk about regulators in ET302 here. Regulators are little chips, usually, that are designed specifically to do this final step. And there are different kinds. We're not really going to focus on them in ET302 here, but if you go on to ET322, we'll talk a little bit more about those at that point. Okay? So these are the building blocks for just about all power supplies. Any questions about these before we go on and talk about the specific power supplies? Okay. Cool. So then, let's talk about some specific real-world power supplies. So this stuff gets a little bit complicated. You don't have to understand every single nuance and detail, okay? There's kind of a lot of information. I'll go through it sort of quickly, but please feel free to stop me at any point if you have questions, okay? All right, so let's start with the half-wave power supply. So it starts off with a transformer, just like all power supplies. And then it goes on to the rectifier. The rectifier for a half-wave power supply is really simple. It's one diode, okay? And then after that, we have the load resistor. We'll call this RL, the resistor that represents the load. The load is the thing that you're trying to power. So if you were charging up a battery, this would be the battery. If you were running a computer, this would be the computer, right? So basically this resistor is just a simplified representation of the thing that you want to actually run, okay? A lot of things can be thought of in one way or another as just a big resistor. So rather than draw the actual thing, we just put in this resistor and we call it the load resistor. Yeah?
Sorry, what is it for?
So, yeah, so I'm getting there right now. So the diode is the rectifier part, okay? So what happens is that we have the AC signal coming in over here. We have another AC signal over here, probably a little smaller because of this transformer. And then we have this diode. So let's analyze how this diode actually works, okay? So basically with an AC signal, there are two conditions that are interesting to us. The first one is what happens when we have a positive voltage on top and a negative voltage down below. So half the time, that's the situation that we're in, right? But the other half of the time, the voltage is reversed. We have a negative voltage up here and a positive voltage down below. So if we can understand what happens in each of these two cases, then we can pretty much figure out how the system behaves as a whole. Okay, so I'm going to look at the first situation first, and then we'll get on to the second one in a minute. So in the first case, we have a positive voltage up here and a negative voltage down below. That means that the left-hand side of the diode, the anode, is more positive than the cathode. So is the diode forward biased or reverse biased?
Forward.
Forward, perfect. So that means the electricity flows through it. And then it comes and it flows through our load resistor, and then it goes back to the negative side of the transformer. So what we can do is we can look at our input voltage and our output voltage and try and see what the two will look like. So we know that the input voltage is like this. Let's say that we had a 10 volt peak signal coming in. Okay. Let's look at our output voltage and see what that would look like. So we know that when we have a positive voltage going in, the electricity flows, so we have a positive voltage across our load resistor. Okay, so the output might look something like this. Now, we're going through this diode before we get to our load resistor. So are we going to get all 10 volts across our load resistor? No, right. 9.4. 9.4, exactly. Because we lose this 0.6 volts across the diode. So we have a 10 volt peak coming in. The output peak is going to be 9.4 volts, right? If we have a 0.6 volt drop across that diode, right? Okay, so that's what happens when we have a positive voltage up here and a negative voltage down there. Questions about that? All right, so then let's look at the second case, right, where we have a positive voltage down below and a negative voltage on the top. Here, we have a positive voltage on the cathode and a negative voltage on the anode of our diode. Is that forward biased or reverse biased?
Reverse.
Excuse me. It's reverse biased. So is the electricity going to flow through it?
No.
No, exactly. So that means that our output is just going to be flat at that point. So when the input voltage goes negative, the output is flat. So our output wave looks like this. We capture the positive half of the signal, but the negative half of the signal is just flat. Okay? So now you guys can see why we call this a half-wave power supply, because it only captures half of our input. Yeah?
Does anything happen to the negative part of the power? I mean,
No, it's just not used.
it just doesn't get used.
Yeah, just gets blocked out by the diode. Yeah.
What would this type of power supply be used for?
Yeah, great question. So we're going to talk about some of the advantages and drawbacks of each of the various types. So one of the advantages of this type of power supply is that it's fairly simple, right? It's only got one component in there for its rectifier. So an advantage is that it's simple. If it only has one component for its rectifier, what do you think that's going to do to the price?
Cheap.
Cheap, exactly. So that's another advantage. So the answer to your question about where this is used is it's used in products that are inexpensive that can get away with it. So let's come back to that in just a second, okay? Let's talk about filtering here for a minute. If we want to look at filtering, basically what we would do is we would put in a capacitor right here in parallel with the load resistor. Okay? And this capacitor acts to smooth out the bumps. Okay? So basically, when the power is going up, the capacitor is charging up, and then in between, the
Discharge.
capacitor is discharging, exactly. And then it charges up again, and then it discharges, and it charges up, and it discharges. So if you put this capacitor in there, you wouldn't see the red and green parts. You would just see this blue line, okay? It would look sort of like this. Okay. Yeah?
If you added more capacitors, would it make it smoother? Or
Well,
does
yeah,
that-
if you had a bigger capacitor, it would be smoother. That's
Okay.
exactly right. Yeah, because it would not discharge as much voltage during the interim, so it would go down less. So yeah, that's exactly right. Yeah.
With the capacitors, do you have to match your capacitor to your frequency?
No, not really.
As far as that charge, they're gonna have different charge times, right?
Right. Yeah, exactly. So you don't have to pick a specific capacitor for a certain frequency, but like you mentioned, the bigger the capacitor is, the more charge it will hold, so the less it will go down. Now, do you think it's good or bad to have these little ripples in there?
Yeah.
Bad, right? Yeah, exactly. We're trying to go for a nice flat voltage. That's what DC is. So these little changes in voltage are called ripple because they sort of look like ripples on a pond. So this is the ripple voltage. So another way of saying that is that more ripple voltage is bad, right? Less ripple voltage is good. So if you have a bigger capacitor, you get less ripple voltage. And that's what you want. Now there's always a trade-off, right? A bigger capacitor is more expensive and it takes up more room. So that's why you don't just put the biggest one in every power supply. But so to go back to your question before, you were asking when or where these might be used. Basically, you have more time between these bumps because you're missing half of the wave. So that gives the capacitor more time to discharge. So that leads to more ripple voltage. So these types of power supplies are used where the product is going to be inexpensive and it can tolerate a little bit of ripple in the supply voltage. Yeah.
How would you determine the size of the capacitor that you want, like the voltage?
Well, so
Is there an equation?
there's not really an equation, but it's I mean, it's something that you would look at in your design. So you would look at the other components in your circuit, and you might be able to tell how much of a change in the supply voltage they could tolerate. And then you could pick a capacitor that would give you that much change in the supply voltage, that much ripple. So if you knew that your components could only tolerate a small amount of ripple, you might choose a big capacitor and pay a little bit more for it, but get that. And then if they could tolerate more ripple, then you could pick a smaller, cheaper capacitor. Yeah?
One of the things the aircraft industry does to compensate for that,
Mhm.
because their instruments are sensitive, is they also have a three-phase,
Mm.
so that whatever time is between the first rise,
Mm-hmm.
you divide that up, so then 2 seconds later, or half a second, nanosecond, get another one.
Right.
And they end up basically with a pure straight line DC voltage.
Right.
Because of the three phases.
Yeah, exactly. So higher frequency signals, like you're talking about, are easier to filter because there's less time for the capacitor to discharge. So, going with three-phase electricity would be one way to do that. We'll see in a minute that other types of power supplies can capture both halves of the signal. And that essentially creates a higher frequency signal as well, because you're getting those bumps in the voltage more often. They're spaced closer together, and so that makes the signal easier to filter as well. So basically, these types of power supplies are used in cheap electronics, something like a desk clock you might pick up at Walmart or something. Something that's inexpensive and not really high precision. Okay? We'll talk about another two examples of power supplies here in a minute, and we'll see that they have slightly better characteristics, so they can be used in higher precision equipment. Okay. So let's talk about the next one. Let's talk about the FullWave rectifier and FullWave power supply. So again, it starts off with a transformer. Now this transformer is special. This is a CenterTap transformer. Okay? We talked about those last time. So, and the FullWave supply uses 2 diodes. So that's what a FullWave power supply looks like. And again, we'll look at the case when we have positive voltage up here, and then we'll look at the case when we have negative voltage up there. Yeah?
So on the halfway, we're not using CenterTap.
Right, the half-wave does not use the CenterTap transformer, but the FullWave does. So, let's look at this case first. Here we have a positive voltage on the left side of the diode and a negative over there. So, is this top diode forward biased or reverse biased? Forward. Perfect. So the electricity flows through there. Then it comes to this junction, and it's got 2 ways to go. So it tries to flow down to the bottom, and it gets to this diode. Is this diode forward biased or reverse biased? Reversed. So the electricity cannot flow down this path, right? It only has one other way it can go. It has to go this way through the load resistor. Okay? And it comes over, it goes around and back to the center tap of this transformer. Okay, so we can look at our input and output voltages again. So again, we'll have an input wave that's 10 volts peak. Now,
Oh,
This is 10 volts from the top of the transformer to the bottom, but we are going from the top of the transformer to the middle. So how much voltage would we have from the top to the middle?
5.
5 volts, right, half, exactly. So we would have half there, and we're still going through one diode, so we're really getting an output voltage, which is 5 volts minus 0.6. So what is the peak of the output voltage going to be?
4.4.
Exactly, 4.4 volts. So we have a positive pump of 4.4 there. And then we can look at the other case where we have a negative voltage up here and a positive voltage down there. So now we're starting off here, and the diodes have voltage like this. So can the electricity go through this bottom diode?
Yes.
Yes, exactly. So it flows along here, comes to this junction up here, tries to go left. Can it go left? No, it's reverse bias. Perfect. So then it comes over here and it goes through the load resistor. So you'll notice with this circuit, the electricity is flowing through the load resistor in both cases, right? Before it only went through in one side, or in one case. Now it's flowing through in both cases. So the output looks like this. We're capturing both the positive and the negative parts of the signal. So the output is capturing both the negative and the positive parts of the input. Yeah?
Yes, what was the point of the load resistor?
The load resistor represents the thing that we're actually trying to power.
Oh, okay.
Yeah. Yeah, so that would be the computer that we're running or the battery that we're charging or whatever. So it's just sort of a stand-in. So, so you'll see we're capturing both the positive and the negative parts of our input. So that's a good thing about the full wave rectifier. One way to say that is that it's more efficient. That's a good thing. And if we put that filtering capacitor in over here, like we did on the other side, on the half-wave supply, then the filtered signal would look like this. Again, it would get charged up and then discharged, but since there's less time between the charging and the discharging, there's less time for the voltage to go down, so there's less ripple. Essentially, it's a higher frequency signal. Okay, so this is another advantage of the full wave supply. There is less ripple than we had before. And that's good, right? We want as little ripple as possible because we want it to be flat. A flat signal would have no ripple. So we're trying to get as close to that as possible. So less ripple. But now what are some of the drawbacks to a full wave supply? What would you say? Yeah.
Real quick, does that essentially double the frequency?
Yes.
So if you had
Yes.
60 hertz, it'd be 120?
Exactly. That's exactly right.
What they use it
What do they use this type of power supply for? Well, so we'll get there in a second.
Advantage is that it cuts the voltage in half.
Yeah, exactly. So that's definitely a drawback. We get less voltage out because we're using this CenterTap transformer, right? So the center.
Oh, sorry.
Oh, go ahead.
I thought you were still looking for negatives.
Yes.
I would say that it's more complex, so there's more additional parts to fail.
Exactly. Yeah. More complex. And what happens to the price when you get more complex? Goes up. So it's also another drawback. It's more expensive. And one of the things that really contributes to the expense is this CenterTap transformer itself. Okay? Turns out it's kind of a hassle to make CenterTap transformers because you have to wind them up, and then you have to go in and you have to sort of scratch the insulation off the middle, and you have to solder something on. So it's more steps. It's a little bit more time consuming. So that adds on quite a fair amount of the overall expense, right? Diodes themselves are not too expensive. They're a couple cents each, but the transformer is kind of a hassle. Yeah.
You said low voltage, so that means you could put like low voltage in the halfway?
Yeah. Remember, coming out of here, we started with 10 volts and we lost 0.6, so we got a peak voltage of 9.4 coming out. Over here, we have 10 volts from the top of the transformer to the bottom, but we're using this CenterTap transformer, so we're going to the center each time, so we're really only starting off with 5 volts there. And then we're losing the diode, so we get a peak voltage coming out of 4.4 rather than 9.4 over there. Okay? Yeah.
Would you normally ground the CenterTap, or would you leave it floating in these situations?
So here the CenterTap would be grounded. Yeah. Yeah.
Can you give more examples what you use it for?
I'm sorry?
I'm trying to get it. So, like, what they use it for?
Right. So what we'll see in a second is that the FullWave rectifiers, FullWave power supplies are actually probably the most expensive, and they're not quite as good as the FullWave bridge rectifiers, FullWave bridge power supplies. So the FullWave supplies are not used very often. Typically, if you're building something cheap that can tolerate ripple, then you use a half-wave supply. If you're building something higher precision, then you would use a FullWave bridge rectifier. So typically you go one way or the other. The FullWave is sort of somewhere in between and not really, doesn't really have the advantages of either one. So this one is used less frequently. Okay. So let's talk about the FullWave bridge supply here for a minute. This one's always the hardest one to draw. Let's start with a pen that actually works. All right, that's better. So we have the transformer at the beginning, like always. And then we have 4 diodes that work together.
Does that have the same type too?
No, this one does not have the CenterTap transformer. So in this case, the load resistor is over here. All right. So this is what a FullWave bridge supply looks like. Yeah.
It's the same thing as a filter, FullWave rectifier.
Yeah, so the only difference is that with the filtered FullWave power supply, we got a capacitor in parallel with the load resistor. Yeah. So again, we're going to look at what happens when we have a positive voltage on top and then a negative voltage on top. Okay? So if we have a positive voltage on top and a negative voltage on the bottom, then the electricity comes this way. Is it going to go left or right?
Right.
To the right, exactly. So it goes down to the right, now it gets here. Can it go down through this diode?
No.
No. Exactly. So it comes over here through the load resistor. And it comes around. And now it reaches this junction. And it can't go up because that diode is reverse biased. So it goes down through this one and to the other side of the power supply. Okay? So it makes this circuit from one side of the transformer to the other.
What allows it, or what makes it go left instead of going right up through that other diode?
At this top part or at the bottom?
There.
Oh, so it always flows towards the
Use resistance.
lower voltage. It always flows from positive voltage to negative voltage. So it's like water running downhill. So up here, you've got a positive voltage and a negative voltage across this diode, so it goes in that way. It does not go this other way because that would be flowing like from negative to positive. That'd be like trying to run uphill. So it goes in the other direction.
So there were two diodes outside?
Yeah, we have two diode drops in this one. Exactly, exactly. So, so we start off with 10 volts peak again. And like you mentioned, we lose one diode drop there and then another one there. So we lose a total of how much voltage?
1.2.
1.2 volts, exactly. But we're starting with the full 10 volts. So our output peak is 10 minus 1.2. That comes out to be 8.8. Exactly. So we get a peak output voltage of 8.8 volts. So not quite as much as the half-wave supply, but more than the full-wave supply, right? So that's good. So now let's talk about what happens with the green case. So we're starting off with positive voltage down here. So the signal starts to flow. We have positive there, negative, positive and negative. So the electricity goes to the right here through this diode, and then we've got a positive voltage and a negative voltage there. So this diode is reverse biased, so the electricity goes over here to the load resistor. Flows through there, comes up and around. Now we've got a positive voltage there and a negative voltage there. So it flows downhill towards the negative voltage, and then it flows back around to the other side of the transformer. Okay? So again, we're going through one diode and two diodes, starting off at 10 volts. So we end up with a peak output voltage of 8.8 volts. Okay? So the full-wave bridge rectifier is able to capture both the positive and the negative halves of our input signal. And we end up with an output signal that looks like this. Okay?
What have you put the
I'm sorry?
What have you put the
Yeah. So, right. So if we put a capacitor in here, like we did before, and we filter the output, again, it charges up when the output is charging, and then it discharges in between when the output is not as positive. So you would get a signal that looks like this blue line if you have the filter in there. Remember, you wouldn't see both of these signals at the same time, you would see one or the other. So if you had no capacitor, you would not see the blue line, you just see a line that has these big bumps in it. If you do put in the capacitor, you don't see this bumpy signal, you just see the blue lines. Okay? So again, you have the higher frequency, right? The 120 hertz. So there's less time in between these bumps than you would get with the half-wave supply. Less time in between means less time for the capacitor to discharge, so less ripple volt, which is good, right? Yeah,
Can you put multiple of these in line?
multiple power supplies?
Yeah, full-wave bridge, like if you wanted to bump up, like wouldn't that make the wave finer? If you're going from 120 hertz to 240 hertz?
Well, so remember the reason that it went, so I like what you're thinking.
Okay, I guess I see how it would work.
Right.
But you could do a full wave bridge and then never mind.
Right.
I
So
see how this works.
yeah, yeah, okay. But I like what you're thinking. Higher frequencies do lead to easier filtering. And remember I said we're not really going to talk about regulators today. When we do talk about regulators in 322, one type of regulator that we'll see creates a very, very high frequency signal. Basically, it takes this signal that's mostly flat and then chops it up into a very high frequency signal and then does more filtering on that. So you're thinking along the right lines. We only use one rectifier because the purpose of the rectifier is to keep the positive half or only the positive part of the signal. So once we've done that, the rectifier's job is done. So, yeah. Other questions? What do they use it for? So with this power supply, we see that it has a lot of the good things that we like about the full wave rectifier and not quite as many disadvantages. So it has the higher efficiency because it captures both the positive and the negative sides of the signal, right? What about the ripple? It's low ripple, right? We said that. So that's good. So what about the cost? This one's kind of a tricky one. What are some thoughts about the cost on this one? Yeah.
I mean, it's still got more components than the half-wave power supply, so it'd be more expensive than that. But since you
Right.
said most of the cost for the full wave comes from the half-tap transformer or the CenterTap transformer, then you're not using one of those, so the
Right.
diodes are inexpensive, so it'd be less than the full wave still.
Yeah, exactly. So the cost is somewhere in between. I'll put a slash there, meaning sort of in between, for just those reasons. So, like you said, it does have more diodes, so that costs a little bit more. The tricky thing is that these power supplies are used so often that this configuration of diodes, somebody saw that and said, aha, we shouldn't make everybody go out and solder up their own set of 4 diodes like that every time they want to make one of these supplies. I know, this is an opportunity. We will make a little chip that has 4 diodes already in this configuration and then just sell that chip to people. Right? So it's less expensive for them because they don't have to do the soldering, and it still makes a profit for the chip makers because they can do it in bulk. Right? So because these diodes can be sold all together in a single package as a chip, that cuts down on some of the expense also. So the cost is sort of, like you said, it's kind of in between, right? Yeah?
So what happens if you put a CenterTap in there?
Put a center tap? Well, it just is not really used, right? I mean, it would be just sort of hanging out there and not doing much. So, yeah.
So what's the difference between like one of these and a switch mode power supply?
So the switch mode power supply really is it uses a switch mode regulator, and that's actually what I was alluding to a minute ago when I was talking about the high frequency thing that chops up the signal. Basically, a switch mode power supply is what most types of electronics use these days. And the first part is really a full-wave bridge rectifier. The thing that makes it the switch mode power supply is the type of regulator that it uses. So it uses a digital regulator that either turns the signal on or off. And when it turns it on and off like that, it creates a square wave. And it does that really, really fast, so that's a high frequency square wave. And then it does some filtering on that that makes a very nice, smooth DC signal. So that's how the that's how that type of regulator works. So this is somewhere in between on the cost front, and then the complexity is also kind of in between, right? Because it's a little bit more complex than the half-wave, but again, this package of diodes comes as a single chip, so it's not that bad. So to answer your question here, basically these are used when you want to have a nice, smooth DC output. So when you are building higher precision electronics, you need a nice, smooth DC output, and you're willing to spend a little bit more money than you would on the half-wave supply. So I would say most electronics these days use the full-wave bridge rectifier, often with a switch mode regulator in there at the end to put that nice final smoothing on the DC signal. Yeah?
Do you lose, again, a little bit of the peak voltage with the switch regulator?
Yes. So all regulators decrease the voltage somewhat. Okay.
Just 'cause it's chopping off that peak, right?
Yeah. So right, exactly. It's smoothing it out, so you wouldn't get it all the way up to the top. There's some inefficiencies in those as well. So they all decrease the voltage a little bit. Yeah.
You can compensate for that by changing the one gains now, right?
Yes, yeah, exactly. So if you chose a different, if you know how much voltage you need to get out, then you can choose the transformer that you're going to use in order to achieve that voltage that you need. So yeah, you can do that, for sure. Other questions? Okay, cool. So that was really what I wanted to say about the half-wave, the full-wave, and the full-wave bridge power supplies. Like I mentioned at the beginning, these are real power supplies that you find in real electronics. So this is exciting because you guys are learning about something that's out there in the real world. Okay? So let me talk a little bit about today's lab, and then I'll let you go in a minute. Oh, yeah, also some homework. So I think I mentioned earlier, but all of the quizzes should now be available to you guys. You should be able to do any of the quizzes, any of the challenge software that's out there. So now is a good time to be working on those and make sure you get them done by the end of the semester. Okay? Also, for homework today, please read in the textbook pages 295 to 300 on inductors. And then please read about capacitors on pages 257 to 267. Next time we're going to be talking about inductors and capacitors. We're actually going to make our own. So please read a little bit about them beforehand, and then you'll be prepared.
Is that in last book?
I'm sorry.
Is that in last book?
In the textbook.
Okay.
Okay, so let's talk briefly about the lab for today. It's going to start off with some multi-sim, so let's go through that as a board. So you're going to go to the instructor files, EC302, and today we're going to do L21 DC Power Supply lab. We'll start off with this first one. Okay, so the first thing that your lab book asks you to do is to record the RMS voltage of the AC generator. Okay? So, do you have to run the simulation to find that voltage?
No, sure.
Exactly. It's listed right there, right on the page. You don't have to do anything. You can just read it right off. So you're going to put that down in your book. You're going to use the DMM to measure the voltage. So you're going to measure the DC voltage first. And this says 15, then it's minus 15 and minus 18. So, excuse me. So why do you think this voltage is bouncing around like that? And is it a big voltage or a small voltage? It's small, right? What are the units on here? Microvolts. So we're talking about 15 or 20 millionths of a volt, right? Very, very small signal. So why would that, I mean, we can see that there's a pretty big signal on the screen here. Why would we be seeing almost no signal on our meter?
It's set to DC.
Yeah, it's set to DC. Exactly right. And DC measures the average of our signal, sort of the middle of our signal. So our signal is above 0 half the time and below 0 the other half of the time. So the middle, the average, is right about 0. So when we measure the DC voltage on the meter, we're measuring the average, and so we're measuring about 0. So some people say, well, how can I write down in my book what voltage it is? Because half the time it's plus 15 and the other half the time it's minus 18, and it's bouncing around like this. I say the important thing is that it's just about 0, okay? It's a really, really tiny signal that's going up just a little bit, down just a little bit, but really the thing to know is that it's just about 0, very, very close to 0, okay? So just pick a value that you want, you know, one of these that shows up on the meter. Don't worry about it too much. The important thing is that it's close to 0, okay? So then we want to measure the AC signal, okay? To measure the DC signal, you push this button, it's a flat line, right? Remember, the DC voltage is just a flat line. To measure the AC voltage, we push this button that looks like a sine wave, because an AC voltage is a sine wave. And when we do that, we see a much bigger voltage, right? 14 volts. So you're going to write that down in your book. And then the book asks you what type of voltage is the DMM measuring. So what it means is, are we measuring a peak voltage or a peak-to-peak voltage or an RMS voltage, or what are we measuring? What do you guys think?
RMS.
RMS, exactly. And we can tell because this voltage that shows up on the meter is exactly the voltage that is labeled RMS on the page, right? So that's a pretty good tip-off. So you're gonna do that, and then you're gonna pause the simulation and draw your wave in your book. Okay. Now you want to be able to see both the positive or both waves. Well, both waves should be the same anyway. So if you want to adjust the scale, you can use these scale buttons to adjust that. Okay, but you really, this is just a single sine wave that you need to draw. I'm sorry. So it's the next one that we're going to draw. All right. So this one, what type of power supply is this?
Halfwave.
Halfwave, right? It only has the one diode. So this is a half-wave power supply. So if we open up our oscilloscope, and we stop the other simulation, now we can run this one. And you can see right now we're seeing the output signal, but we're not seeing the input signal. The reason for that is that the input signal is on channel A and the coupling is set to 0. So that just means that it's always 0. So we'll change that to DC. Now we can see the input and the output signal, right? The input signal is in red. You can see it's going positive and negative, and then the output signal is in blue. We're capturing only the positive halves of the signal, okay? So you're going to draw that in your lab book, and note that you're capturing only the positive halves of the signal. Then we will go on and do the next circuit. So what type of power supply is this?
FullWave page.
Exactly. So you're going to run this power supply as well. Actually, the next one says PS3A. So the next one is going to be this one. So this is the half-wave supply with a filtering capacitor in it, right? So we can run this, and right now we see this red wave, which is the input signal, but we're not seeing the filtered output signal. Okay? The reason for that is that the filtered output signal is near the top of this red wave, and so it's off the screen right now. So we need to adjust the scale so that we can see the output there. So we'll adjust the scale for channel A, put that up to 10 volts per division, and we'll do the same thing for channel B. And now we can see the input and the output signals. So the input is this red sine wave like before. The output is now the blue wave. Yeah?
It's kind of difficult to see the blue wave. Is it
Oh, I'm
possible
sorry.
to change the color of
Yes.
the waves on there?
Yes, it is. So one thing we can do is we can hit this reverse button. Yeah, so now the background is white, yeah. So, so now you can see the input is red, the output is blue, and so the output is charging up when the input is positive, and then it's discharging as the output, or as the input is low, okay? So this is the filtered output. Any questions about that? Okay. So then we're going to look at the filtered output from a full wave signal. Again, it's going to be somewhat similar. We can change the scale. So then we can also change the time per division. So it's sort of hard to see, but the output is actually being charged when you have a positive peak and also when you have a negative peak. Okay, so you're getting charged up in both of these cases. So that's good. So the output is actually a little bit flatter because it's getting charged twice as often. Okay. So you're going to set this up, and you're going to measure the output signal, and you're also going to do this. You're going to do this with different size capacitors. So you're going to use a big capacitor here, and then you're going to put in a smaller capacitor. You're going to just double-click on the capacitor and change the rating from 1,000 microfarads to 100 microfarads, and you're going to see what effect that has on your output.
So like you said, tell us what capacitor we have to use?
Yeah. It says to do it with 100 microfarads and with 1,000 microfarads. Yeah. Okay. So that's it for the multi-sim. Any questions about that? Okay. So then after that, you're actually going to build a real half-wave rectifier on a breadboard. Okay. So let's take a look at the lab book here. I'll bring it up on the screen for just a minute and we can see what's going on. So this diagram at the top shows you how you're actually going to construct the circuit. You're going to start with a transformer. This is one of those black blocks that plugs into the wall that has the 3 holes in it for the banana plugs. So you're going to get one of those, and then you're going to hook it up to a breadboard. You're going to hook one side of a diode to one side of the transformer, then you're going to plug in a resistor across and have the other side of the resistor go to the other side of the transformer. These TPA and TPB, that stands for test point A and test point B. So this is where you're going to hook up an oscilloscope. So you're going to need 2 leads for the oscilloscope. The first lead, the probe for the lead is going to connect right there, and the ground plug is going to connect right here where it says ground. With the second lead, you're going to connect the probe right here where it says TPB, and the ground for the second lead is also going to go to the same place as the ground for the first lead. Okay? So you're going to build this, and then you're going to look at the signals on the diagram. So one signal, the signal from test point A, will be your input, and you'll sketch that up here. And then the signal here at test point B will be your output. You'll sketch that down on the bottom of this graph. Okay. So that's going to be the unfiltered signal. The second part of the lab, you're going to add a filtering capacitor. So you're going to put the capacitor in parallel with your load resistor here. Okay? Now, you're going to be using the electrolytic capacitors, so please be careful and plug them in the correct direction. Because everybody remembers, you plug them in backwards, they explode. All right? We actually had this happen in the last lab. So please be careful and plug them in the correct direction. All right? And then you're going to sketch the output. We're going to do that with I think again it's a 100 microfarad or a 10 microfarad capacitor, and then with a 100 microfarad capacitor, and you'll look at the difference on these 2 graphs. Okay. So that's all of the circuits that you're going to build. And then there's just a few questions that you'll answer at the end, okay? On that page and then up here. So, any questions about the lab? Yeah.
Just to make sure I understand, so building the circuit, that component is labeled 1N4001?
Yeah, that's the diode.
Okay.
So that's this guy up here. Remember, the diodes are labeled with a stripe on one side. That side corresponds to the cathode on a CenterTap. So this little marker here represents the stripe on the diode. Yeah. Other questions? All right. Cool. Then let me take roll, and I'll let you go.